gravitational lensing. What the hell is gravitational lensing? I'm wondering. Well, it's the bending of light, essentially. That's what it is. But let's go with the formal definition, because I'm not going to put words in their mouth. I want them to put words in my mouth here, right? Okay, let them hear it from the horse's mouth. Okay, here it is. Here's the European Space Agency and NASA. This is what they have for gravitational lensing. It goes more or less like this. Gravitational lensing occurs when right? It's an occurrence. It's an event, phenomenon. When a massive celestial body, such as a galaxy cluster, causes a sufficient curvature of space-time for the path of light around it to be visibly bent, as if by a lens. The body causing the light to curve is accordingly called what? Gravitational lens. Okay? And I want to focus on that word path. Okay? Because this is going to be the key word here throughout the lecture today. Path can be an object, like a dirt road or a trail or a road, whatever, a highway. Or it can be a verb, the itinerary, the trajectory. And mathematical physics likes to confound words. They like to mix them and say it's a verb object. It's an object verb. In other words, they use the word path in both ways in the same sentence. And that's what I want you to focus on as I go through the lecture today, okay? Keep in mind the word path. Okay, that's going to be the tricky one. And it says, according to Einstein's general theory of relativity, time and space are fused together in a quantity known as spacetime. Within this theory, massive objects cause spacetime to curve, and gravity is simply the curvature of spacetime. As light travels through spacetime, the theory predicts, it's going to do some predictions here, that the path, taken by light will also be curved. What are we talking about? Path curved? Well, it looks like, are they talking about a road? Or are they talking about an itinerary? What's being curved? By an object's mass. They're going to curve the path. Okay? Gravitational lensing is a dramatic and observable example of Einstein's theory in action. Extremely massive celestial bodies, such as galaxy clusters, cause spacetime to be significantly curved. And that's interesting because spacetime is a concept. It's four number lines, which they call coordinates or dimensions, depending on the day of the week. And they say these number lines are curved. That's great. So how do you curve a number line? Is a number line a thing that you can curve like a banana or a hammock? In other words, they act as gravitational lenses. When light from a distant light source passes by a gravitational lens, the path of the light, again, the path of the light is curved. Are we talking about an itinerary slash trajectory, motion? Or are we talking about a road, trail, highway? What are we talking about here? What do you mean the path is curved? And a distorted image of the distant object, maybe a ring or a halo of light around the gravitational lens, can be observed. Okay? So that's, in a nutshell, the definition or the notion of what a gravitational lensing is. It's a phenomenon, okay, that they observe, the astronomers see out there, a little light around a halo, so to speak, galaxy behind a galaxy, a star behind a star, that sort of thing, okay. And here we have an illustration, okay, and let me turn this on. I think this is from the Wikipedia. So just watch. There's no sound here, but you can see what they're referring to when they talk about gravitational lensing. It's just an illustration of how light from a galaxy from behind shines around a galaxy that's in front of it. And so they say what's happening, light is curved by the mass of the galaxy that is between your eye and the faraway galaxy. So here it is, just an illustration, a little GIF here. You can see the background and the foreground galaxy there. And you can see what happens to light. You're going to curve it, okay, to your eye, to the detectors here on Earth. Okay, and that's essentially what it is. Okay, so it's just the curving of light. Okay, it's just the curving of light around a galaxy. Very simple concept. I don't think you need to know much more than that about this gravitational lensing. You have something behind another. You have an eclipse right? You have a umbra, penumbra, whichever, one behind another. And you can see this thing, or the halo at least, through a galaxy that's in front of it, that is eclipsing it. Why? Because they say light curves. Okay? That's the explanation. That's the physical interpretation for why we see that. Okay? So they're explaining a phenomenon. They're giving you a physical interpretation. They later on, when you put them against the wall, they say, oh, we don't give physical interpretations. That's not part of our job description, mathematical physics. And so they dismiss all that stuff. Well, do you or don't you? Well, they do, because otherwise their equations are worthless. So they have to turn it into some kind of physical interpretation, some kind of explanation, some kind of mechanism, cause. Okay? They have to give you that, because otherwise their equations are worthless. Just that simple. Okay, so here we have it. Fellow everybody knows, his name is Matt O'Dowd. He works for people at PBS. Okay, and he gives you an idea of, what this gravitational lensing is all about. Listen to him carefully. Okay, I'm going to just mouth the words that he said. So I'm not putting words in his mouth in a way, but it's what he said. I just said it with my mouth. Okay, here goes. In the real universe, both space and time can be curved. The curvature produced by mass gives gravity. The path traveled by light follows the curve. And so gravity bends the path of light. Good old Matt O'Dowd, he is a caricature of a scientist. He's not a real scientist. He just parrots what the establishment, fed him. That's what it is. And so, what can I say? These are the people who talk on the internet. There's tons of them. There's only little old me against all of them, so there's tons of them. And of course, they're going to give you the party line, that's all. But they cannot explain a single phenomenon. And they admit that they cannot explain a single phenomenon. Or as Richard Feynman said in the 60s, he said, physicists or mathematical physics has given up on that. They don't give physical interpretation. They give you an irrational one. When you call their bluff, they say, well, we don't do that anyway. It's not part of our job description. It's not our line of work. So why did you give me a physical interpretation if it's not in your line of work, if it's not part of your job description, your everyday duties? Okay? Why did you give me this BS interpretation? And I'll tell you why. If they don't give you a physical interpretation, their equations are worthless. That's why. And again, they could be doing equations for jumping rabbits, and maybe what they're looking at is a torquing snake. So that's another thing. Well, anyways, good old Matt, he mentions one of the first guys to prove, that Einstein was right regarding this, light bending, okay? And this is the picture that is so famous out there in 1919. There you see one of the articles that came out in those days, okay? It says, lights all askew in the heavens. Men of science more or less agog over results of eclipse observations. Okay, Einstein theory triumphs. That's when Einstein became a big man. He got his Nobel Prize 2 years later. Okay, partly because of this, right? He got it for the photoelectric effect of 1905 that he mathematized, you could say. And but he was also given it because of this, because his prediction came true and people were changing their minds about how the universe works. Okay. So it says there, stars not where they seem to be. Okay, yeah. And but nobody need worry. Yeah, okay. So anyways, the point here is that you can see the halo around the eclipse of the sun, and that halo is a star behind the sun. Okay? And so they said, hey, Einstein was right. Light does curve around, okay, around the sun. When there's an eclipse, you can see it there. You can see the glare of a star that's behind the sun. Okay, so this is what they showed, okay? that light curves around. In fact, the sun's light curves around the moon there. You can see it there as well. So I guess we're all, in agreement. Light seems to curve around the sun, right? And so keep in mind two words. One was path, okay, and the other question you need to compare is curved. We can put warped there. We can put bent there as well. Versus deflected. Does light curve or is light deflected? Okay, keep that in mind. We're going to get back to that. Okay, so here's my illustration of what Mr. Eddington had in mind. Okay, there's some kind of wall. Okay, maybe it's not on the outside, but it is in a way, because what they're saying is that the sun weighs down space-time, creating those walls in space-time, and the little photon or the wave, whichever, has no other choice but to slide around or drift or roll around those curved walls made by the sun. So you don't have to think of this as gravity pulling towards the center of the sun. You have to, which is what Newton suggested. You have to think of this as the sun weighing down space-time, warping the walls through which the photon has to slide. So the walls are on the outside, okay, not on the inside. Very important. And this is essentially what Einstein proposed, and this is what we have even to this day, that this is the explanation for why light curves. The sun weighs space-time downwards, and the photon has no other choice but to slide around in a curved space/space-time. Okay? Essentially, they're warping time, whatever that means. They're warping time. Okay? Okay, so here we have, because of these ideas, you have the first one here. We call them idiots. What's an idiot? Idiot's a person with big ideas. Okay, so we call them idiots because they don't have little ideas, they have idiots. We call them idiots. Okay, here's one of the conclusions from these idiots, and this comes out of the Wikipedia. It says that point particles can also curve space-time. I guess they should if they're point particles and they have, I guess, mass. That means every particle in the universe, keep this in mind, okay? Every particle in the universe is weighing down space-time somewhere. So space-time is not a smooth thing, as they always show you, this canvas is full of potholes. And I mean, not just one here and one there. I mean, all of space-time is just practically covered with potholes, because every little thing weighs space-time downwards, I guess, downwards, whatever downwards is out there, Okay, so every little atom in the universe is weighing down space-time. That's the proposal by general relativity by Mr. Einstein. Okay, so they're saying it all weighs everything down. Okay, and so yeah, the point-like particle, right, assuming it's got some mass, I guess, weighs down space-time, and that means light never should travel straight, or rectilinearly. It has to go through all these little potholes every step it takes. You wonder how poor old light does this. I mean, not even God designed such a monstrous world. This is just beyond our imagination. But that's what they say. A point particle, what is it? Lacks spatial extension. Okay, so there's nothing there. It weighs something. That nothing weighs something, meaning it weighs down space-time, and by doing so, it deflects the path of light. Every step light takes, it's deflected. You try to explain that, okay? So light never travels in a straight line in general relativity. It can't, because all masses weigh down space-time. Every atom. Okay, so here we have another group of idiots. Big ideas, right? Here it is, and they say that because of this, right? Does light travel straight or curve? Well, let alone light, even the Earth, they say. In 4D, the Earth orbits around the sun in a straight line. In a straight line. In 4D space, the projection of a straight line onto a 3D volume is still a straight line, but it may have some oscillations due to the presence of a fourth spatial dimension. So there you have the rational orbit that normal people, even people in the ancient days you knew about, they were aware that the earth goes around the sun. And these people say, no, you're wrong, Bill. Our relativity gurus tell us something different, that the earth and the moon travel straight, and I guess they go outside the solar system. I mean, I don't know what they mean by straight. Okay? But they say that in 4D they travel straight. And since everybody says that we do live or exist in a 4D space-time here, I guess the one on the left is out of bounds. It's wrong. The moon and the earth travel straight. Now you know it. You heard it here first. Okay, so we have all these people, they have all these irrational conclusions, all these irrational explanations, physical interpretations, mechanism, causes. They have all are irrational. The words coming out of their mouths are all irrational. Okay, the way they express themselves. Maybe they just need to better their language, no problem. But then work on the language. Don't tell me that the Earth travels straight in 4D space-time, but it curves here on Earth. What the hell does that mean? What can it possibly mean? Okay, and the same with light. Earth, doesn't matter. Okay, gravitational lensing is essentially the same experiment or observation out there in space as the experiment here on Earth known as the slit experiment. Here you have straight light, and it curves around the sun because space-time is warped by the presence of the sun, right? And so, you get this curvature of light according to general relativity. And that's more or less what happens in the quantum world with a slit experiment. The light goes straight, but somehow on the other side of the slits, you have all these waves. They curve around, they begin to interfere with each other. So you go from straight light to curved light. So all these people see in curves. They say everything is curves. And, we do have an explanation for the slit experiment, which more or less has a little to do, it's going to be the same mechanism we propose for gravitational lensing. So here's the illustration of our mechanism of how the rope explains this. And what it is that, you have essentially a light source, and all the ropes are connected already to everything else. And so if you put not a pair of slits, you put, some kind of needle, something like that, okay? You put something like that in front of it, and the question is, if you have photons, little particles, they should go straight out. They have nothing to bounce against and come back in. And that's the way mathematicians illustrate the slit experiment. It hits the walls of the slit and then bounce inwards. But if you have no walls of slits, if you only have something in the center, how do you produce the coming back in of that whole beam? What's it bouncing against? Why does it come back in? Okay? And in this case, why does it produce these waves, these transfers or whichever waves they want? I mean, it doesn't matter. They can produce longitudinal transverse waves, doesn't matter. But how does it come in? Why don't they just continue going straight if there's nothing to bounce against to come in, back in? There's no sill, no window sill, in other words, right? Where to bounce against. Okay, and so here's my needle experiment, and what I did was I put a laser pointer. You can do this at home, very cheap experiment, not $1 billion experiment. You put a laser pointer, and you put farther down, a few meters down the road, you put a chair with your cork, and a needle stuck to the cork, okay? And you're going to shine the laser pointer exactly at the needle. You got to, position it there so that it hits the needle. And on the fore wall, you will see fringes, which is what Thomas Young saw for the first time. In fact, apparently Newton was the first one to carry out that experiment according to Thomas Young. He says that in his book, okay? But here it is. I carried out this experiment some years back. I think it's still valid, so here it goes. Watch it carefully. Here you can see the laser pointer, okay? And then another chair, I put a needle stuck to a cork, okay? And then farther down the road, you can see some light out there. So I'm going to go to that light now. Okay, you can see what the light does, what it is. all static, so nothing's moving, and you can see the fringes there. Okay? Okay, very straightforward. You can do this at home, prove it to yourself, okay? You don't have to believe my word, okay? So the question is, you can produce fringes with a needle. You don't need slits. You don't need two slits. And then if you don't have the slits, you don't have anything for light to bounce against and come back in. If you need the bouncing without the slits, without the window sills, right, the frames, it'll just go straight. It should go straight. There's no reason for it to come back in. But it does. But as you can see, with a needle, it curves around the needle. And so that's like in the case of gravitational lensing. Are we saying that the needle is weighing down space-time and that's why it curves light around with, needle, how much does it weigh? 1 gram? And it curves light around because of all that weight? Or like the other guy said there, point particle also weighs down space-time, it bends space-time. That's why light curves inwards, because you're bending space-time around the needle. You see the issue? Okay, those are questions for you to ponder. Okay, so what's the big problem? Well, why do we have this problem with gravitational lensing and the slit experiment and all these other good things? Entanglement, you can also include in there, etc. Language. What's called word salad, semantics, what these people dismiss as, oh, you're doing a semantic argument, Bill. Yeah, we're doing a semantic argument. No, the guys doing semantic are the other people, not me. I'm trying to define my words. I'm accused of doing semantics. No, it's the people who use the words wrong who are doing semantics and word salad and word wizardry. Okay, so here it is. This is the problem. What is a mathematical physicist? An individual who doesn't understand the difference between an adverb and an adjective. Okay? Here are the verbs, common verbs that mathematicians, typically confuse for nouns. Itinerary, it's not a noun, not in physics. Orbit, orbital, motion, trajectory, path, energy, charge, number, mass, force, field, time. None of these are nouns in physics. In physics, it's got to be an object to be a noun. Okay? That's the only one that can serve as the subject of a sentence. Those are the only nouns allowed in physics. Okay? It's not the orbit of Jupiter, it's Jupiter orbits. Orbits is what it does. And then you have ether, wave, plasma, electricity, singularity. What is a singularity? Space-time, black hole, dark matter, function, conscience, and tesseract. These are just some of the words. I could go on with more. These just came out of the top of my head. Okay, what's an adjective? A qualifier or modifier of a noun or of an object. In physics, here we're talking about an adjective for the purposes of physics. Okay, we're saying that what qualifies a physical object. That's what we're talking about. It's what is, right? Not what it does. And there you see, straight, curved, bent, finite, infinite, continuous, bound, flat, warped, perpendicular, segmented, inert, exists, 2D and 3D. If something is three-dimensional, that's an adjective of an object. On the other hand, we have adverbs. Those are qualifiers of verbs, motions, and concepts. Primarily concepts, we say, but we put those in there so that you know what we're talking about. It's about what it's doing, not what it is, but what it's doing. And it refers to motion primarily. And there you can see some of the adverbs, which are treated as adjectives or who knows what, or sometimes not used at all. Deflected, diverted, swerved, incessant, ceaseless, perpetual, constant, curvilinear, rectilinear, dead, alive, living, being, and 4D. Four-dimensional, what is that? Means time. Time had better involve motion, and hopefully a 4D entity is something already in motion. You cannot say, well, I cannot imagine a four-dimensional space-time like Mr. Hawking said. No, of course he cannot, because he's talking about motion, he's talking about a concept, he's talking about a dynamic concept, and he's trying to imagine a physical object. So this is where we start. We start with language. We have a problem with the language that these people use today. And we're going to see some of the problems that these confusions that these people have, or misinterpretations, what they cause in physics. Okay, they cause enormous problems in communication. And it's them who are doing word salad because they're treating all these words in an irrational manner. Okay, it's not wrong, it's irrational. Okay, okay, so what is light? Here we have it. Okay, we have straight transverse electromagnetic wave. That's what we thought a wave was, at least all the way till Maxwell, right? And now we're starting to curve light around. You know, I don't know how many beers these guys drink, but they curve light around. Okay, and they say it curves around the sun. So are they warping the wave? I mean, don't we need to know if it's a wave or a particle for that matter, right? Here's a wave, and you're bending it, you're warping it, you're turning it around, you're curving it, okay? And so the question here is, are we going to say that a wave is curved or that it is deflected? Are we talking about something in motion which is taken out of its itinerary? I won't use the word path because it's very confusing. Are we taking it out of its trajectory? Is that what it is, which means it's deflected? Or are we talking about a physical object that is curved like a banana, like a hammock or whatever? Are we talking about a continuous object here for the wave? Is that what a wave is? Okay, does the wave of light stretch from here to Andromeda uninterruptedly? Or does it flow like a little boat from Andromeda down here? You know, a little wave that moves little by little, you know, all the way down here. So we need to establish that. Are we talking about, is the wave interrupted at some point? Is there a beginning to the wave, an end to the wave? You know, outside the atoms, I mean, because if it has a beginning in an atom over there and it stretches or extends uninterruptedly all the way to my eye, then yeah, the wave connects my eye to that atom. Okay, do we understand that? Okay. Otherwise, it travels like a little boat, like a sailboat. You know, a little wave just emitted, and ciao, you're good riddance. You know, you're out. So you got to determine whether the wave is continuous all the way to Andromeda Galaxy, extending all the way down there, or if it travels the wave. You know, they always give you a piece of a wave. You know, several links. I'd like to know if the wave stretches uninterruptedly from Andromeda to my eye. Okay, and this is the other version. This is the particle version. Okay, straight line again. They really are referring to rectilinear travel, not a straight line, but they turn these verbs and adverbs into adjectives and nouns. That's the problem. Okay, I mean, are we talking about straight line or rectilinear trajectory, rectilinear itinerary? What are we talking about? You know, are we talking about all these particles moving? Is that what it is? Or are we talking about a straight line? See, that's not a line. That's a bunch of dots. And if each one is location, one of the two, either there's one dot that is occupying all those locations, or there are all those dots occupying each one its own location. And I guess they all move forward or something. You know? So you got to determine what you mean by straight line of photon, which is what the term they use. And then you have the bent line, which is a curvilinear or curved line, they call it, right? Or a warped line. So again, you know, are we talking about a line, or are we talking about a whole bunch of apples? Okay, if a whole bunch of apples, you got also to explain, you know, why, what causes it to bend like that, to warp like that. And they say, well, because space-time is bent or warped by the sun, and then the photon has no alternative but to slide or roll along warped space-time. That's the explanation we receive. Okay, if that's the case, then space-time has to be a physical object. You cannot later say, well, we don't know what space-time is, or space-time is not an object, it's a mathematical concept, because you're warping a thing to give me a physical interpretation. So you cannot later deny what you just said. Okay, otherwise these people live in contradiction, or they give you what they always say, well, we don't do that, that's philosophy, that's interpretation, we don't do that, we do equations. If you do equations, stick to equations, don't try to bluff, don't try to, your way, don't try to convince me that you understand how this universe works, that space-time is warped and you've proven it with so many experiments. No, you got to make sense of that. If you can't make sense of it, then don't give me any physical interpretation. Just stick to your equations and stick them up your nose holes also, because they have no importance in physics. In physics, we don't use equations. In physics, we have to explain the mechanism. Okay, that's what people want to know. People want to know why this spoon, falls to the floor. That's all you need to explain. You tell me what causes that to go to the floor and not to the ceiling. Then we're done. But don't tell me that space-time is warped and space-time is, you treat it like a physical object, then deny and say, well, we don't understand it anyways, it's not part of physics anyways, and then why did you do that? Why did you try to convince me that space-time is warped? Okay. Because otherwise your equations are worthless. That's why. Okay, so here we have Mr. O'Dowd again. Put him up there. So again, so he says, and so gravity bends the path of light, and the path traveled by light follows the curve. Okay, so he concludes that gravity bends light. Okay, but again, you got to explain it. He's just describing that, and that's his interpretation, that's his opinion, but he has no justification for what he's saying. Right? So he's a caricature of a scientist. He's not a scientist. Scientist is someone who can tell you why. Okay, and if he's going to say that this is caused by warped space-time because that sun weighs, space-time downwards, then he's treating space-time as a physical object. He cannot later deny it and say, well, I was just only kidding. I was giving you an analogy, and you're not supposed to take it literally and all that good stuff that mathematicians, the arguments they created over the years. Because that's what they do. They give you one to show you that they know and that you don't. They're going to educate you, and then you say, well, yeah, but space-time is a physical object. Well, you weren't supposed to take it literally. It's not a trampoline. It's not a canvas for real. It's the way we explain our mathematics, bring it down to your peasant level. The question is, who's the peasant here? Is it the listener or the guy giving the dissertation? Okay? And then here we have our conclusions. We can say, here it is, questions to ask a mathematician. Okay, these are our conclusions. Is light a flow of particles? Or is it strung out waves? They extend forever, the waves? Or do the waves travel as a little sailboat, meaning they're discrete waves, meaning it's a wave packet? What is a wave? Does wave get broken at some point? Is it cut off from other waves? That's one of the questions you need to answer. And then you need to know what a particle is. Is it a value? Is it a magnitude, an amount? Is it a number followed by a unit? Is that what a particle is? Or is it a corpuscle? Is it a ball? We're going to talk about balls, or are we going to talk about, values, mathematics? Okay, that's important. Are we talking physics or are we talking math? Okay, and they never do that. They want to put both of them together, call it mathphyz, mathematical physics, right? And again, is light a wave or is it but if you look at the wave, it's a bunch of vectors, magnitude and direction, that's a number. So is a wave just a bunch of numbers, a magnitude with direction? What is this? What is a wave? Okay, it's a description, mathematical description of something. And they represent it with this, vectors, and they move the vectors around. They show you this wave in front of you, say, okay, I understand it's a physical object, right? Because I see something in front of me that's got shape, it's moving. No, what you're staring at is a mathematical concept that they're moving. Bunch of vectors, okay? Magnitude and direction, perpendicular to each other. How do numbers go perpendicular to each other? How do numbers have direction? How do numbers flow? Okay, so we need to establish what light is. Is it a wave? Is it a particle? What do you mean by particle? What do you mean by wave? That has to be up front. If you can't begin that, you cannot enter physics. You cannot begin your dissertation in physics. These people jump in the middle of the show and say, well, you know what a wave is. It's that thing that's moving there on the screen. No, I don't understand what I'm looking at. I'm looking at a bunch of vectors that are moving, numbers that are moving. Whoa. How much did you drink today? Bartender, I want what he had. Okay, and then we have, does light stretch uninterruptedly from Andromeda to Earth? If you're talking about particles, you can say, well, the particles travel. So they're all discrete, so they're not connected to each other. Why would they travel in a straight line or in any way for that matter? That's one issue on the one hand. But if they're waves, the question is, does that wave stretch all the way to your eye? Wave, no interruption? Or is there a sailboat, a little wave packet that just travels through the air, through space, or whatever. You got to determine that. Okay, so, and then is the meteor of light made of a single piece, or is it made of parts? I mean, are we talking about particles, or are we talking about single piece, meaning, if the wave is made out of a single piece? This wave, whatever the wave really is, okay? Does light bend, warp, curve, or does it deflect? If you're talking about photons, what do you mean you're bending a photon? What do you mean you warped light? What do you mean you warped or bend or curved light? Are you saying you curved the photon? Or are you saying you deflected the photons with warp space-time? Okay, so they're not clear about that. They use adjectives, and they use them to give a physical interpretation in which they're talking about adverbs, okay? In physics, not in ordinary speech, okay? Adjectives qualify nouns. So if you're going to say curved, warped, bent, they're talking about a physical, the table can be bent, or broken or warped or whatever. That's different than saying that a whole bunch of photons are traveling in a curved manner. No, they're traveling curvilinearly, rectilinearly. They're deflected. You can use any term you want, but make sure you use the right terms. That's why it's an issue of language. And these people are saying, "Oh, light is warp." What do you mean light is warp? What is light? Is light a single solid thing that you warp, or are we talking about the deflection of photons? That has to be clarified. The language is absolutely essential to understand what these idiots are saying. Okay. If so, what was it that bent? Right? Those are the questions you got to ask these people. Don't ask me these questions because I don't do mathphyz, So whoever does mathphyz has to defend his position. I defend something else. Okay, so here we have it. Illustration of that. Here goes. You can see, are we saying that the wave travels like a little sailboat, or does it extend all the way to Earth? Okay, that's the question. If it extends and it continues, otherwise you got to tell me where the wave begins, where it stops. Okay, you see that? So it either travels or it extends. One more time there. Okay, so you need to know the beginning and ending of a wave. Okay? So, these are the things that people have to, these are the questions, the structural questions, the assumptions, the hypotheses that people have to question. And mathematical physics doesn't have any because they don't have definitions and they don't have objects. They deal with concepts which they converted or morphed or reified into concrete things, into objects. And they treat them as objects, field, mass, energy, etc. And they treat them as physical objects. And then they apply adjectives to what in front of us is patently a verb. So they should be applying adverbs, and they don't. They apply adjectives because an adjective goes well with a physical interpretation. Adverbs talk about motion. So they don't say that something is incessant. They say it's unbounded. They don't say that, or they use the word path, which is ambiguous. You can say, what do you mean by path? Well, I mean that it could be, a road, a highway, or it could be the itinerary of you on that road, on that highway. So if the highway is curved, you curve. No, I don't curve. My itinerary is curvilinear, not curved. What's curved is the highway. And so you have to distinguish between warped, curved, and bent on the one hand, which are adjectives for objects, and itineraries, or trajectories, which can be deflected or incessant or perpetual. They have other qualifiers which are known as adverbs in physics. You have to determine if you're talking about an object or a verb. And once you determine that, you got to use an adjective for these and adverbs for that. That's how it is. Okay, that's physics. Okay, so how do we do it under the rope model? Here it is. The rope extends all the way to Earth. Okay, and then with this we can explain. And here it's only one atom on each side. Okay, we have gazillions of them. But here again, one rope only, and you can see why the moon doesn't fly away, because it's every atom. The moon is tied to every atom on Earth, And that's why you can see the moon at all times. You're seeing through these ropes. It's the torsion going in both directions. And then you see the difference between quantum and the rope model. One is just discrete particles, and the other one is interconnected ropes. One more time here, you see the rope, one rope only here. You can see different frequencies there. Okay, the moon going around the Earth also, because every rope connects every atom on the moon to every atom on Earth. And there's the difference between quantum mechanics and what we propose. Okay, straightforward. Okay. Okay, and so here, just in case for those of you who have doubts, more proof, more evidence. Those of you who want evidence proof, you know, here it is. We have Mr. Richard Muller, and he says, what? Every atom on Earth is connected to every atom of you. You are also connected to it. Let's repeat that. Let's see if you can get that in your head. Every atom on Earth is connected to every atom of you. Every atom of you is connected to every atom on Earth. That's what Muller is saying, professor at UC Berkeley. Okay? Now, what part of that did you not understand? It's straightforward. Let's repeat it one more time, all at the same time now. Every atom of you is connected to every atom of Earth. Every atom of Earth is connected to every atom of you. How else can you explain that unless there is a physical connector which you cannot see or touch? Okay? And you say, see, touch? Yeah, because an object, a thing, is not that which you can see or touch. It's that which has shape. This connector, this mediator, this agent that we put in between atoms has shape, but it cannot be seen or touched.